All right, so let's take a look at the product rule first. And we're going to go one at a time here. And so I have an example to do with each of these. So this is how you could set up your paper. You can set up your paper by writing down what we're doing first. It's the product rule. And then write the general formula, which is that d dx of f times g. Now what does d dx mean? Yeah, it means the exact same thing as f prime of x. D over dx is just another symbol that means take the derivative. So let's take the derivative of two functions being multiplied by each other, because that's what product is. Product just means multiplied. And it turns out the answer is, and very important that you would say this verbally, the derivative of the first times the second plus the derivative of the second times the first. That's how you take the product rule. The derivative of the first times the second plus the derivative of the second times the first. Now you probably noticed that I wrote that down a little differently from how it is in the yellow right there, but it's still essentially the same, right? Do you see f prime g plus f g prime? Yeah, I think that this way is just more helpful. That's the way they put it in the textbook, but this is the way I'm giving it to you in a way that's nice to verbalize. So let's practice verbalizing it. Everyone repeat after me. The derivative of the first times the second.
The derivative times the first times the second.
Yeah, the derivative of the first times the second. One more time. The derivative of the first times the second.
The derivative of the first times the second.
Good. Plus the derivative of the second times the first.
Plus the derivative of the second times the first.
Yeah, there you go, there you go. Verbally, it's so helpful if you can put those words in your mouth and in your brain so you remember what to do. Because that's what we're going to do as we start doing actual derivatives. So here's our example. G of x is equal to 4x cubed minus 11 times x plus 3. Now, honestly, it doesn't really matter if we think, okay, which one's f, which one's g. I mean, I can go ahead and label it. This one will be f, and this one will be g. It's much more helpful to say the derivative of the first times the second plus the derivative of the second times the first. So let's do that together as we verbalize it, okay? So here we're about to find g prime of x. We are about to do the product rule. So here's the product rule in English. The derivative of the first, so what's the derivative of this thing? 12x squared? 12x squared? Right, because 4x cubed, the derivative of that, 3 times 4 is 12, minus 1. So 12x cubed, the derivative of 11 is 0. So the derivative of the first times the second, and just write it down. Right, the derivative of the first one times the second one. So the second one does not change at all. Plus the derivative of the second one, well, what's the derivative of x plus 3? It might help to put a 1 on the x. What's the derivative of 1x plus 3? Remember, this is just a linear function, so the slope is just
X.
1. Yeah, so just 1. The derivative of x plus 3 is just 1, because the derivative of 1x is 1, and the derivative of 3 is 0. Perhaps we should review a little bit that the derivative of any number times x is just a number. After all, what's the slope of the function y equals 1x plus 3? Just the number 1. So the derivative of the second, that's just 1, times the first. 4x cubed minus 11. So did we do it? Is this the derivative of the first times the second plus the derivative of the second times the first? Yeah. Now already, folks, that's the answer. All right, we're done. That's the answer. That is the derivative. But what should we do? Simplify. Right? From here on in, this is just algebra. This is just simplification. We did the derivative. So now we simplify. I'm going to distribute and distribute. So that gives us, what, 12x cubed plus 36x squared plus 4x cubed minus 11. We can simplify further by doing what?
Combine like terms.
Yeah, combine like terms. So we have the 12x cubed and the 4x cubed. So that's 16x cubed plus 36x squared minus 11. So that is the derivative. Now, so that was an example of the product rule. That's the product rule. Anytime at all that you have two things being multiplied together, you take the derivative by doing the derivative of the first times the second plus the derivative of the second times the first. Now, you might say, are we right? It's always a good question to ask. We just did something. Are we right? Well, what can I do besides leaving this as two binomials being multiplied back together? What can I do to this to simplify this? I could FOIL it, right? You don't have to do this with me. I'm just going to show you. This would be 4x to the fourth plus 12x cubed minus 11x minus 33. Did I do that right? 4x to the fourth plus 12x cubed minus 11x minus 33. Yeah, that's g of x also. Right? Isn't that still the original g of x function? Now, can I take the derivative of that doing the normal power rule? This is now just the normal power rule, because I can take the derivative of each term by term by term. So what's the derivative of 4x to the fourth? 16x cubed. And what's the derivative of 12x cubed? 36x squared. And what's the derivative of negative 11x? Just minus 11. And what's the derivative of negative 33? 0. Did we get the same answer? Yeah. So that's nice. That's nice. That tells us that even though we're learning this rule, it's just a rule, it's a shortcut. It's a shortcut. So you can do the shortcut rule, or instead of doing a product, you could just FOIL it together, get a polynomial, and then do the power rule term by term by term. Which way takes more effort? Well, it depends on your perspective. Right? Maybe you like this way better because you're like, hey, just FOIL it, then do the power rule needed. But every once in a while, we have two things being multiplied that aren't both polynomials. And you won't always just be able to FOIL that together. You'll have to do the product rule. So there's our first rule. It's called the product rule. Derivative of the first times the second plus derivative of the second times the first. So now you have a nice little reference sheet for that on your line sheet of paper. You can carry that around with you, put it under your pillow, keep it in your pocket, share it with your friends and loved ones. Okay, let's take a look at the next one, the quotient rule. Is the quotient rule as simple as the product rule? I mean, just looking at it. What does the quotient rule have in common with the product rule? And in fact, I'll write them down side by side. Here was the product rule, f prime g plus g prime f. And here is the quotient rule, f prime g minus g prime f over g squared. Did I get that? Yeah. So what's the same about it? What's different about it?
Addition.
Yeah, the product rule is addition. The quotient rule is subtraction. What else is different? You're dividing by g squared. Is that the derivative of g? That's just g squared. Notice the derivative are just the ones with the prime mark on it. That's f prime. That's the derivative of f. That's just g, normal g. So f prime g minus g prime f all over g squared. So that's the difference between the product rule and the quotient rule. They have very similar components, except the product rule you're adding, the quotient rule you're subtracting, and then you divide by g squared. Okay, so folks, we're going to go ahead and implement this rule, but to do so, I'm going to teach us a friendly trick. So everyone, first, will you write down the quotient rule with me? So this is the quotient rule. This goes on your line sheet of paper. And we're going to take the derivative of f over g. And before I actually write down that formula, I want you to write something else just below it. This is, I can't help myself but share this with you. This is something that I learned back in the day when I studied calculus. And any calculus class, you'll learn a fun little mnemonic or a song that you can tell yourself to memorize a particular rule. And the way this rule works is, if you all will just listen and watch real quick. Well, actually, I'll say it first. Hody-hi minus Heidi-ho over ho-ho. That's what you're all about to say. Everyone say it with me. Hody-hi minus Heidi-ho over ho-ho. Okay, so Hody-hi minus Heidi-ho over ho-ho. Try the whole thing. Hody-hi minus Heidi-ho. Yeah, isn't that nice? It just rolls off the tongue. All over ho-ho.
All over.
Yeah. Now, some people say high-low. Low D high minus high D low all over low low. But I always learned it as ho-ho. It's kind of like Santa Claus. You know, ho, ho, ho. Okay, so here we go. So it'd be ho D high minus high D ho all over ho ho. So that's the particular mnemonic that we're using. Ho D high minus high D ho all over ho ho. And so now, keeping that in mind, allow your eyeball to move up and down from high to low or high to ho. And let's write down the rule. So ho D high, right? Ho D, D meaning derivative. Ho D high minus high D ho all over ho. Wait a minute, did I just write that down wrong? Hold on a second, oh my gosh. O D high. Oh, D high. Oh my gosh, guys, hold on a second. I can't believe I just wrote it down wrong. What's wrong with me? Oh, because it's derivative of the next one. Oh my gosh. It's O D high, as in the derivative of the high, minus high D ho all over O. Oh my gosh, I'm so sorry. Here you are on this nascent stage, about to write down the formula for the first time, and I write it down wrong. Yeah, O D high, as in the derivative of the high. Oh, I'm so sorry. Yeah, O D of the high, so the derivative of the high one, minus high D of the low, derivative of the low one, all over O. Oh, that means I wrote down the ho D high thing wrong too. What's wrong with me? I've been doing this for years, and all of a sudden I write it down wrong. The correct thing would be O D high minus high D ho all over ho ho. Folks, let's all leave the room and come back in. I'm just kidding, don't get up. But I can't believe I just told you that whole formula wrong. And the whole purpose of telling you that was just to give you some way of memorizing it. And perhaps I could have just said memorize the formula. But I wanted to share this phrase with you. Okay. So now let's actually try it. Oh, I'm mortified, guys. I'm mortified. Let's try this out. Our function, it says y equals. So our function is y equals. Oh, this is a terrible function. Folks, we just cross out that x. Just cross it out. We're not going to do a function like that. We're going to write down x to the fourth plus 4 all over. Now, do we have to write down 3 plus 16x cubed, or can we write down 16x cubed plus 3? Let's write down 16x cubed plus 3. Okay. Clearing our minds. We've got this new quotient rule, O D high minus high D ho all over ho ho. And we have a function, x to the fourth plus 4 over 16x cubed plus 3. Okay, let's try it. So, I'm going to go ahead and now, I'm going to write down y prime. Instead of doing f of x and f prime of x, you could also have y and then y prime. So, our rule states ho, which is going to be the 16x cubed plus 3, times d high, the derivative of the high, the derivative of the top. So what's the derivative of the top? The derivative of x to the fourth plus 4? 4x. Yeah, just 4x cubed. So, ho d high, as in the derivative of the top. Minus, that was ho d high. Minus high, that's x to the fourth plus 4. D ho, the derivative of the bottom. What's the derivative of the bottom part?
48x.
Yeah, 48x squared. All over ho ho, which is 16x cubed plus 3, and then that whole quantity squared. So this was O D high minus high D ho. There we go. That should have been how I told it to. O D high minus high D ho all over. Okay, so folks, the good news is we're already done. That is the derivative. It is the derivative, but what should we do to it? Simplify. So we'll go ahead and distribute the top. So we can distribute that 4x cubed to that one. So what is that? 64x to the 6th plus 12x cubed. That's the first part. But then we have to subtract this part. I'm going to put it in parentheses because we're subtracting. You want to put it in parentheses to be very sure that you're subtracting every term inside. So now that's 48x to the 6th plus 192x squared all over 16x cubed plus 3 squared. This is a good best practice. Make sure you leave the two expressions in parentheses with the minus in between. That way you can very carefully minus those terms. So now what do we have? We have 64x to the 6th plus 12x cubed minus 48x to the 6th and then minus 192x squared all over 16x cubed plus 3 squared. And then what can we do?
Combine like terms.
Yeah, we can combine like terms. So our final answer for this one would be 64x to the 6th. Nope, sorry, gotta subtract those. 64 minus 48.
That's 16.
16, so 16x to the 6th plus 12x cubed minus 192x squared all over 16x cubed plus 3 squared. Now, technically, is there anything else we could do to that numerator?
Yeah,
What?
we can pick out, say, 4.
Yeah, I think we can take out a 4. Is that correct? Let me just check. Divided by 4. Yeah, we can take out a 4.
4x squared.
And an x squared. So technically, our final answer simplified would be 4x squared outside of 4x to the 4th plus 3x minus 48 all over 16x cubed plus 3. But keep in mind, what we're doing now is just simplifying. We're just simplifying. We already did the hard work of the derivative early on. The derivative, the ho-de-hi minus hi-de-ho over ho-ho, that was the first thing we did. From here on in, we're just simplifying, simplifying, simplifying. Do you think there's anything else we can do? Do you think we can factor that? 4x to the 4th plus 3x minus 48? Don is optimistic. I'm not optimistic because that's an x to the 4th and that's just an x. Maybe had it been x squared and x, maybe we could factor, or maybe it had been x to the 4th and x squared, maybe we could factor, but I don't think this one does. Okay, so anyway, that's it. That's the quotient rule. I am, again, mortified that I messed up my presentation of the quotient rule. I will continue to say ho-de-hi minus hi-de-ho over ho-ho for the rest of this class and for the rest of my life. To help me remember. Yeah, no.
So for the test, you're going to want us to simplify all the way down.
Yeah. Yeah, you always want to simplify as much as possible. Okay, the next and last rule is called the quotient rule. Sorry, I just said quotient rule. The next and last rule is the chain rule. So I'm going to start, this is the next part of your paper, chain rule. Now, I don't recommend you write that down. See, every once in a while I disagree with the textbook. While that is correct, there's a lot of stuff that we don't need there. What we want to do is take the derivative, dx, of a composition, f of g of x. We want to take the derivative of a composition. So first of all, let's just remind ourselves, what does a composition look like? You all remember doing compositions in previous classes and even in this class? Like let's say that I had f of x is 2x minus 3 and g of x is, we'll just say the square root of x plus 5. Then what would my composition of f of g of x be? We want to put the g function into the f function. So I would write my f function very big, 2 times something minus 3. And what am I plugging into f? G. So this would be a composition. Right there. That's a composition. I could go the other way and say, what's g of f of x? Because when you switch the order of composition, it's normally different. So now I'm plugging f into g. So I would write down g first. That's the square root of something plus 5. And what am I plugging into my g function? F. So I would plug in 2x minus 3. And then I can actually combine like terms a little bit. And I have 2x minus 3 plus 5 is plus 2. And then that would be the composition. So I just did this quick example to remind us what a composition is. In a composition, you have an inside function and then an outside function. Does that language make sense? You have an inside function and then the outside function? That's really important. So let's go back to our chain rule and what we're going to write down. Which one is the outside function? F or G? Yeah, F. F is the outside function. And G is the inside function. So the chain rule goes like this, and I'll say it in English as I write it down. If you want to take the derivative of a composition, you take the derivative of the outside function, leaving the inside function alone. That's the verbiage. Take the derivative of the outside function, leaving the inside function alone. Then multiply by the derivative of the inside function. I'm going to say that again multiple times, and then I'll write it down in English. That's called the chain rule. So, now in English. Take derivative of the outside function, leaving the inside alone. Then multiply by the derivative of the inside function. That's just formulaically what we have there. So in order to use the chain rule, what we have to do is look at a composition and clearly identify the outside and the inside so that we're able to accomplish that. So look at what they gave us. They gave us y is equal to 4x cubed plus 15x squared. So what is, in this example, what is the outside function and what's the inside function? What's the outside function?
Power of 2.
Yeah, the power of 2. Exactly right. The outside function is the fact that we're just taking something and we're squaring it. That's the outside function. And what's the inside function?
4x.
Yeah, 4x cubed plus 15x. So the outside function is the fact that you have this whole parenthesis thing being squared. And the inside function is the 4x cubed plus 15x that's actually inside that parenthesis. So visually, it's really important that we're able to distinguish that so that we can then proceed to actually do the chain rule. So let's go ahead and try it. I'm going to, now we're taking the derivative, so I write down y prime. Now we're going to take the derivative of the outside function. Well, first of all, everybody, let's just remind ourselves. What is the derivative of something squared? What do you do with that power?
Move it down.
Move it down out front and then subtract 1. So is that the derivative of the outside? That's the derivative of the outside. So let's take the derivative of the outside and leave the inside alone. So we're just going to leave the 4x cubed plus 15x right there. We're just going to leave it. I should keep on going with my colors here. There. So did I take the derivative of the outside and leave the inside alone? Yeah. And then now what do? We multiply times the derivative of the inside. So what is the derivative of 4x cubed plus 15x? Yeah, 12x squared plus 15. Yeah, that's it. So that's the chain rule. You take the derivative of the outside, leaving the inside alone, and then multiply by the derivative of the inside. Now, we're done. That is the derivative. Now we just have to clean it up. So in order to clean this up, I would say, well, 2, and then 4x cubed plus 15x times 12x squared plus 15. Well, now you got a hard choice. Like on the one hand, I could pull an x out of this, right? So then I would just have 2x outside of 4x squared plus 15 times 12x squared plus 15. Oh, I shouldn't have written that second part down yet. What else can I take out of the 12x squared plus 15?
3.
I can take a 3 out of there. So I'm going to move a 3 out here. And so now I also have 4x squared plus 5. There. So what's my final answer? 6x and 4x squared plus 15 and 4x squared plus 5. And at least that way it's factored. It's factored as much as we can in its current state. What's the other way you could present this final answer? Could we FOIL it all together and make it a polynomial?
Yeah.
Yeah, that'd be the other option. You can multiply the whole darn thing together and then just present it as a polynomial. You know, something x to the 5th plus something x to the 4th plus something x cubed and on and on.
I have a question.
Yes, Rosa.
So like the 2x before you put in the 2x
Yeah.
times 4x squared would be 2. Would it be 8x?
Yeah, if you had distributed that 2 in, it would have been 8x cubed plus 30x.
Okay.
Yeah. All right. Well, folks, these are our 3 basic rules. Product rule, quotient rule, and chain rule. And now we're going to go ahead and try and practice those today. And that's our day. We're going to look at these 3 different rules. So now you have your line sheet of paper, so you can practice. And here we go. We're all looking at number 12. So number 12, we have f of x is equal to negative 6 to the 8th plus 3x to the 5th times 70 to the x minus 1. So first of all, which rule are we looking at? Product, quotient, or chain?
Product.
Yeah, product. We got something times something. Second of all, we should review real quick what the derivative of e to the x is. We haven't done any problems like this yet, but it's on your formula sheet. The derivative of e to the x is e to the x. E to the x is the one special function in the universe whose derivative is itself. And so the other thing we should know is that whenever you take the derivative with a constant out in front, what does the constant do? It just comes along for the ride. So the derivative of e to the x is e to the x, and the 5 just comes along. So the derivative of 5e to the x is just 5e to the x. That's 2 different rules there, though. The first rule is that the derivative of e to the x is e to the x. It's the one function in the universe whose derivative is equal to itself. The second rule is that whenever you have a constant in front of a function, that constant just drops down to the next line. You do the derivative of that function, and the coefficient comes along. Okay, so now we're prepared to try this problem. Oops, sorry, that's f of x. So how do we do the product rule? Let's verbalize it again. Derivative of the first times the second plus the derivative of the second times the first. So let's go in order. Our derivative f prime of x will be the derivative of the first. So what's the derivative of the first? Negative 48x to the 7th plus 15x to the 4th. Did everyone get that for the derivative of the first? Times the second, so we just got to write that down, 70 to the x minus 1. Derivative of the first times the second. Plus the derivative of the second. Well, what's the derivative of the second term?
7.
It's just 70 to the x, because the derivative of 1 is 0, and the derivative of e to the x is e to the x, and the coefficient comes along to the right. So the derivative of the second times the first. And again, that is the answer. If you type that into mat213, it will accept it because it is correct. Is it simplified? Not so much. It would be possible to simplify this further. I think for right now, I'm going to let us just leave it like that because I know mat213 will take it, and I want us to focus on the product rule and not get bogged down by all the algebra of simplification. So we're done. That's the product rule. That would be the derivative of that function. So let's try that again. Number 13. So number 13, our function is f of t equals t squared is 4t plus 3 times 7t squared plus 3. Did I get that? Yeah. So what rule is this? Product, quotient, or chain? It is the product rule. How are we so sure that it's a product rule? I mean, first of all, is it the quotient rule? No, I mean, we're not dividing. And is it the chain rule? Yeah, we don't have an inside function and an outside function. So it's not the chain rule. It's definitely the product rule. Okay, so here we go again. The derivative of the first times the second plus the derivative of the second times the first. So derivative of the first. What's the derivative of the first? 2t plus 4. Hey, the derivative of the first times the second what's the derivative of the second? What's the derivative of the second one? 14t, and that's it? Times the first. T squared plus 14. Okay, that's the product rule. That is the derivative. It is the correct answer. If you type it in mat213, it's correct. If you typed it into Desmos, it'd be correct. Now, can you all simplify that? Sure you can. You'd FOIL it and both out, distribute, combine all your like terms, and then it would be simplified. Again, for now, let's go ahead and just keep on moving and just focus on applying our rules. You can always simplify later.
It wants us to find that prime of 3.
Oh, thank you. Thanks for pointing that out to me. I didn't notice that. Find f prime of 3. How do we do that? You just plug it in. So f prime of 3. We can do a lot of this in our head. So 2 times 3 is 6 plus 4 is 10. And then 3 squared is 9 times 7 is 63 plus 3 is 64. And then 3 times 14 is 52. And then 3 squared is 9 plus 12 is 21 plus 3 is 24. And you would multiply and add all that together. So f prime of 3 is,
We're going to be 10 times 66.
did I do that wrong?
Yeah.
9 times 7 is 63. Oh yeah, 66. Thank you. So that would be 660 plus 52 times 24. Did anyone else get 1908? Now, folks, here's a good question. What does that mean? It's f prime, so what are we talking about? Yes, the derivative, which on a graph, what are we talking about? It's slope. And so what is the slope? It's a fraction, 1908 over 1. So what does that mean? Up 1908, right 1. How steep is that? That's incredibly, incredibly steep. What should we expect the graph to look like at f prime, at 3? What should the graph be looking at over at right then?
14 times 3 is 42.
Oh no, did I do all those calculations wrong, Ashley? Thank you for telling me that. Where did I go wrong? 3 times 2 is 6, is 10, is 4. Sorry, it's 10, and then 9, 63 plus 6 is 6. Which one? 14 times,
42.
it's 42. All right, but then it's 24, and then 42 times 24. Oh my goodness, guys. I apologize.
Today's just not even good.
Yeah, so far, not my day. Okay, 1,008 over 1. Is that correct, Ashley? Okay, good. Thank you for checking me. Okay, in any case, it tells us that the graph is incredibly steep right there. And so, what would we expect to see if we graphed it? Pulling up Desmos. The original function, by the way, was x squared plus 4x plus 3 times 7 x squared.
I
Plus
think
3.
the answer is 1,668 because you add the 660.
Oh boy.
Yeah.
10 times 66 plus 42 times 24. 1,668. All right. I am never skipping steps ever again. I'm just going to get out my calculator and do it the proper way. All right. And so what should the graph be doing at x equals 3? Do you guys all see the graph? Look at this weird graph. It is a very strange, very skinny graph. And what happens to x equals 3? Well, first of all, x equals 3 is way up there. If I even want to get to x equals 3, I have to go really high up to even get to x equals 3. And what is the graph doing? It's incredibly steep. It's incredibly steep. So this is correct. This answer that we got is correct. That when you look at x equals 3, the graph right there is incredibly, incredibly, incredibly steep, which is what we just found out by calculating a slope value of 1,668. Fingers crossed.
Final answer.
Yeah, final answer. I should phone a friend. Which you guys were my friends by helping me. Okay. So thank you, Don. Let's go on to the next one. So number 14, is this product, quotient, or chain? This one is also product. So what is this, number 14? So we have g of x is equal to x squared plus x plus 2 all times e to the x. And just to make this easier on my eyes, I put the e to the x in parentheses, just to really make it clear to me that I have two things being multiplied together. So it's the product rule. Okay, so applying the product rule. The derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first, what do you get?
2x.
Yeah, 2x plus 1, because that's a 1 on the x. Times the second, so 2x plus 1 times e to the x, plus the derivative of the second, what's the derivative of e to the x? E to the x, times the first, which is x squared plus 1x plus 2. All right, so that already is correct. That's the answer, it's the derivative. However, this one we can simplify quite a bit. And I want to show you folks an elegant way to simplify this. Now, what you might think to simplify is distribute the e to the x and then combine like terms. We're not going to do that. Instead, what we're looking at here is two expressions that both have an e to the x being multiplied by it. So instead of distributing the e to the x, what we can do is factor the e to the x out in front of the whole thing. Is that fair what I just did? This is a simplification technique we'll use quite a bit in this class because we do encounter functions with e to the x in it quite a bit. And so instead of distributing the e to the x into both of those parentheticals, you can just factor the e to the x out in front of the whole thing. Now, is what I just wrote, is it correct? Given my luck for the day, you might think no. But is it correct? We factored it out, yeah. And how would I check? I would just distribute it back in again and see, oh yeah, that would put an e to the x next to both of them. So now that I pulled the e to the x out, what can we do? we can combine all those polynomial terms very conveniently without being bogged down by all those e to the x's everywhere. So what do we have? X squared plus 3x plus 3. Now that looks good. That's nice and simplified. It didn't take a ton of nasty distribution or FOIL or anything like that. What do you notice about the original problem versus the derivative? We started out with a polynomial times e to the x. What did we end up with? A polynomial times e to the x. So that was interesting. But the basic structure of the formula preserved itself. So that's our g prime of x. Okay. Well, I think that's it for product rules. Yep, quotient rule. So let's write it down very carefully. So this is number 15. We have f of x equals 7x to the fifth, x to the fourth,
Minus 3.
minus 3x cubed, all over
X more.
x to the fourth. So we're going now, product, quotient, or chain?
Oh.
Definitely quotient rule this time because it's a fraction. So we're going to implement ho d high minus high d ho all over ho ho. So let's start with ho d high. So ho, and then the derivative of the top. Ho d high. So what's the derivative of the top?
35.
35x to the fourth
Plus 32x
plus 32x cubed minus 9x squared.
squared.
All right. So that was just the ho d high. Ho times the derivative of the high. And then what? Plus or minus?
Minus.
Minus I d ho. So I, next, x cubed, d ho. And the derivative of the bottom? 4x cubed. All over ho ho. So x to the fourth squared. Now again, that's the derivative. In order to simplify this, we would have to distribute everything in combined like terms. That would be the only way out, or the only way to simplify. So what do we have then? 35x to the 8th plus 32x to the 7th minus 9x to the 6th. And then minus, you have to be very, very careful that you're minusing each of those terms. So minus 28x to the 8th minus 32x to the 7th, and then plus 12x to the 6th. All over, what's x to the 4th to the 2? What's x to the 4th to the 2? What's x to the 4th squared?
60.
It's to the 8th.
Oh, to the 8.
Then you multiply. When you raise an exponent to an exponent, you multiply. Okay, and now we combine all of our like terms. And so what do we end up with? We have 35 minus 28, that's 7x to the 8th. And then, ooh, look what happened to the x7th term. Was that exciting? Yeah, it was exciting. Remember, calculus is algebra with lots of cancellations. Every once in a while, you get excited and you have a cancellation. And then plus 3x to the 6th all over x to the 8th. Did I simplify that correctly?
Yeah.
Folks, that problem is an excellent example of the phrase, sometimes things have to get worse before they get better. Have you all heard that phrase in life? Sometimes things have to get worse before they get better. That's often the case in calculus because you do lots and lots of algebra with lots and lots of simplification. What's another way we could have done this quotient rule? Did you notice what we could have done right up front if we wanted to? What could I do?
Component.
I could break this into 3 different fractions, couldn't I? And so my 3 different fractions would be 7x to the 5th over x to the 4th, and then 8x to the over x to the 4th, and then minus over x to the 4th. What would have happened had I done that? Look at how so many of the x's cancel out. That would be a 7x. Those cancel out. That'd be an 8. And then most of those cancel out, and that's a 3 over x. Would that have been another way to do this problem? To just immediately transform it into that? Which I could then write as 7x plus 8 plus 3x to the negative 1. You know, instead of doing the quotient rule, to check your answer, you could go ahead and just simplify your fraction. Now, what's the derivative of 7x? Just 7. What's the derivative of 8? 0. And what's the derivative of this one? You bring the negative 1 down, so that's minus 3. And then subtract 1 to the negative 2. And so now this is the derivative, which is 7 minus 3 over x squared. What answer did we get? What happens if I go ahead and create 2 different fractions? 7x to the 8th over x to the 8th. And then, oh no. Somehow I have a sign wrong. That would have been minus, minus, plus. Well, that's 3x to the 6th over x to the 8th, which that would have both canceled out. We'd have had 7 plus 3 over x squared. Oh, that was a minus. That's a minus. Therefore, that's a minus. Therefore, that's a plus. There. So did we get the same answer?
Yeah.
We sure did. Okay. Well, that was that one. So that was a quotient rule. Let's try another quotient rule. This one, a little simpler. So we have x equals 4x plus 3 over 2x plus 2. Before we do this quotient rule, can we just simplify it like this in different terms? Would that be helpful now?
No.
Not so much, because the denominator is a binomial. The denominator has 2 terms. So even if I wanted to think about it, don't write this down. If I wanted to do 4x over 2x plus 2 plus 3 over 2x plus 2, is that really an easier problem? No, now I have to do the quotient rule twice. Now I'd have to do Hody high minus Heidi ho over ho ho here, and then Hody high minus Heidi ho over ho ho here, and that's a longer problem. So no, that wouldn't be helpful at all. Instead, we should just keep it the way it is and go ahead and do the quotient rule. So, what's the quotient rule? Daniel, what's the first part of the quotient rule?
It is the Hody.
Yep, Hody high.
Hody
So
high.
ho, and then d high. So what's the derivative of the top?
4.
Just 4. And then
And then high, low.
minus
Nice, high, low.
high d low. So high d low. What's the derivative of the bottom? 2. All over?
Low, low, low. So
Low, lower. Oh, yeah. 2x plus 2. Square. Thanks, Daniel. Okay, did we do it? That was the quotient rule. Ho d high minus high d ho all over ho ho. So ho d high minus high d ho all over ho ho. And now what do we get to do with all that? Simplify. So we would distribute and distribute. So it gives us 4x, no, sorry, 8x plus 8, and then minus 8x, then minus 6. And our 8x's cancel out, and we have 2 over 3x plus 2 squared. What are we really tempted to do right now? You're kind of tempted to cancel the 2's, right? Can we cancel the 2's right now? Technically, no, because this denominator is being squared. Well, what could we do? Well, that's a 2 over 2 times x plus 1 squared, right? So then what do we do? Since we're squaring the 2 times x plus 1, put that in, aren't we? Because it's going to be 2x plus 1 times 2x plus 1. So that's really 2 times 2 is 2 squared times x plus 1 squared. Is that right? So now we have 2 over 2 squared times x plus 1 squared. Now can we cancel a 2? Now we can cancel a 2. We can cancel one of the 2's from the bottom with the 2 on the
How
top.
did you get the x plus 1?
Because I factored a 2 out of 2x plus 2.
Okay.
Yeah, I just factored a 2 out of it. That's all I did in that step, was factor a 2 out. And then when you have an exponent outside, you multiply the exponent times both of the inside exponents. And so now I can cancel out that 2 and one of those, and I end up with 1 over 2x plus 1 squared. Is that right? Okay, well, we have 2 more quotient rule to practice, but I think what I'd like to do is just do one of them with you, and then we'll move forward and we'll start practicing the chain rule. So I think I'd like to leave number 17 for you. So you can just circle number 17. You can do that one on your own. So let's do number 18. Find the derivative of g of x equals e to the x. Now, when you see an expression like 2 plus x, what are you tempted to do? Instead of writing 2 plus x, write it down as x plus 2. I don't know if you guys also feel that way. But whenever I see a polynomial written out of order, I like to rewrite it back into the normal order of decreasing powers of x. You don't have to by any means, but I just like to. Okay, Daniel, thanks for doing the last one. Wendy, how do you do the quotient rule? Okay, so O, D high, what's the derivative at the top? Yep, derivative of e to the x is e to the x. Yep, high, and what's the derivative of the low?
1.
Yeah, the derivative of 1x is just 1, and the derivative of 2 is 0, so just 1. All over? Oh. Great. Now, we've already seen this trick once. What do we do when we have 2 different expressions that have an e to the x on it? Yeah, you can factor that e to the x all the way outside. So now instead of, I have x plus 2 and then minus 1. Did I factor the e to the x out correctly? Did I factor the e to the x out correctly?
Mhm.
Okay. Okay, so now I can actually combine like terms in there, and we have e to the x outside of what? X plus 1? All over x plus 2 squared? And that's g prime of x. That's the derivative.
So the x plus 2 cancel out because that's the x is 1.
This is x plus 2 minus 1. Even though there's parentheses there,
Yeah.
yeah, so that's just x plus 1 on top.
Okay.
Okay. All right. So The reason that there are two separate packets for 2.5a and 2.5b, I believe 2.5a just covers power rule, product rule, and quotient rule. So that's it for 2.5a. 2.5b is practicing the chain rule. So that's the second packet that you all picked up today. So this is good timing. Let's take our break. And then when we come back, we'll start looking at the chain rule. So it's 12:02. Let's start again at 12:11. James, there you are. Were you hiding in the back of the room this whole time?
No, I had advisory meetings.
Can't get around those advisory meetings.
No, I had to be roped in and it went longer than I expected.
These things happen.
So I apologize for that.
Oh, yeah, man. You gotta do what you gotta do. Well, that's it. Yeah, you can just put James. Sure.
Thank you.
I don't know. I'm excited to know what it is. Ya para la otra semana me dicen, "Hey, what did you read?" Por esto. Hoping for a girl, you know. Oh, lo que Dios me quiera mandar, pero quiero otro niño. Yeah. Like my sister has girls and like just a disaster with it. Like this weekend, like we went to Mexico, y todos días en niños. Oh my god, like the girls were like such a thing. Like nomás fuimos unos fines de semana. No, it's too much. Ya, como 5 maletas la mujer. No me voy para aquí, but because then una girl la renta también a un boy. You know, like, just showing you showing no know the after she like after I'm just like y era una maleta de la ropa mía de un poco de mi vida que lo que fue feliz y al niño le echó por cambios y me yeah because those cambios al día pero ella lleva como 3 cambios al día yeah. Y un niño de sucio no se iba a tomar. Like, un niño todo chorreado no se iba a tomar. Una manchita no se iba a tomar. Como un niño así. Con los shoes, like, puedes ponerle una yellow shirt y sus black shoes y no se mira mal. Y una niña no puede ponerle una pink shirt y unos blue shoes, you know, like, yeah. So, por eso veo otro niño. There's so much easier. It's harder for parents to buy them clothes because there's less. But yeah, and like so, yo cuando miro algo bonito y tengo dinero, like lo compro luego because if I say, oh, I'll come back next time, like you don't find it. I don't find it. Yeah. Y yo lo que tiene ahorita.
All right, folks. What I would recommend everybody do is have some sort of a reference sheet. Just like I created right here. You would benefit from having something like this out in front of you all the time. And the way I have the formula up here, the formulas, is how I'll be verbalizing them in class. So either writing something like that down on a sheet of paper, or just coming up here later and taking a picture of that, and then making your own reference sheet later on. You can put it on an index card. You can tattoo it on your face. Whatever you'd like to do, so long as you're carrying that around with you and you can see it at all times. So the next section that we're looking at is 2.5b, and that's just the chain rule. That's it. This whole unit is just on the chain rule. So let's start by writing down the chain rule. Right up at the top of your paper, the chain rule states that if you'd like to take the derivative, d dx, of a composition, f of g of x, again, verbally, you take the derivative of the outside function, leaving the inside function alone, and then you multiply by the derivative of the inside function. The reason they call this the chain rule, and you don't have to write this down, but let's just say you had some sort of ridiculous composition of 4 functions. What if you did f of g of h of j of x? I don't even know if I did the right number of parentheses there. But so it's a composition of a function inside a function inside a function inside a function. That's like, what's that movie with? Inception. Yeah, there's a dream within a dream within a dream within a dream. So if I were to do the chain rule now, it'd be the derivative of the outside function, leaving the inside g of h of j alone. But then I multiply by the derivative of the inside function. Well, the derivative of the inside function is the derivative of g, leaving the inside alone. And then since there's an inside function, I'd have to multiply by the derivative of the inside function, which would be h prime, leaving j alone. And then I'd have to multiply by the derivative of the last inside function, which is that. And so perhaps now you can see why they call this the chain rule. Why is it called the chain rule? And again, you don't have to write that down. It's just something to kind of look at. Does it look like a link of like links of chains, like chain links? Like you make a paper chain where you have one link, then another link, and then another link. That ends up what's happening. Terms get chained together through multiplication. What would be a better name for this, though? Maybe the Russian doll rule. You know those Russian dolls where you take off the top of the Russian doll, and then there's another small Russian doll inside. Then you take that out and take the top off of it, and then there's a smaller Russian doll inside. You know what I'm talking about?
Yeah.
I think this would be better if it was called the Russian doll rule. But they call it the chain rule because the terms get chained together through multiplication. Okay, so that's our chain rule. Let's go ahead and take a look at this first one. It says, use the table to find h prime of 1. So before we start looking at the table, let's just consider h of x. Everyone just write down h of x is really equal to f of g of x. So we're just saying that h is some function that happens to be a composition of two other functions. And let's go ahead and take the derivative. So h prime, if I take the derivative, that means we'll do the chain rule. So by definition, you do the derivative of the outside function, leaving the inside function alone, times the derivative of the inside function. So that's what h prime is. So far, that's just the definition of the chain rule. And what would they like us to find?
1.
Yeah, just plug in 1. So I'll go ahead and first write it empty. H prime of something equals f prime of g of something times g prime of something. And so what value will I plug in?
1.
1. So I plug in 1 there, and there, and there. Well, now we can go ahead and start looking things up in the table. So what can we look up? What can we look up immediately? We can look up g of 1. So here's g of x, and I want to look up g of 1. So what's g of 1?
1.
Just equal to 1. So now I know that g of 1 is equal to 1. So right here, I'm going to put a 1 right there. And then what's g prime of 1? I come over here, here's my g prime. Here's 1. G prime of 1 is equal to 3. So now I have, out there is 3. Well, now I can go ahead and look up the next value, which is f prime of 1. So here's my f prime of 1, and that's equal to 2. So now I have 2 times 3, which is equal to 6. I have no doubt that that might have felt very awkward or weird. Perhaps that particular activity you've never done before in your life. You know, looking up multiple numbers from a table and then plugging it all in. Yeah, it's super weird. But just for fun, let's go ahead and find h prime of 3. How would we find h prime of 3? First, again, we would write down h prime. So h prime was f prime of g of something times g prime of something. So how would I find h prime of 3? So what can I look up first?
G of 3.
G of 3? I don't know. So there's my g function, there's 3. So g of 3 is equal to?
3.
Actually 3. So g of 3 is 3. And then g prime of 3, we can go look that up. So now g prime of 3 is equal to 2. So that's a 2 out there. But now I can go ahead and look up f prime of 3. So f prime of 3 is equal to 1. And so that's 1 times 2, which is equal to 2. Admittedly, that's a very strange activity. It's a very strange activity, but I think they include it in there because it's just a careful, slow, step-by-step procedure where you're focusing on the individual parts and pieces that you're actually doing. How many total computations are you actually doing to compute a chain rule? 3, technically, because you have an inside function here, which once you compute it, then you can compute the outside function. But then you also have the outside function here. So every chain rule is really 3 computations, and I think that's the purpose of that exercise. Okay. Let's try the next one. And again, let's write it down again. So we want to find the chain rule. So the function is 3 negative 8x cubed minus 5x to the 8, all to the power of 18. Did I get that correct? Okay. You folks aren't writing in colored markers, but if you were, I would recommend that you do something like this. That you rewrite it now as the outside function, which is 3 something to the 18th, and the inside function, which is negative 8x cubed minus 5x to the 8th. So now it's very obvious what my outside function is versus my inside function. So how do we do the chain rule? You take, so go ahead and say Wendy for us.
Take the derivative of the outside function,
Leaving,
the inside function,
and then?
multiplied by derivative of.
Yeah, very good. The verbiage there is very important. So let's take the derivative of the outside function. So what's the derivative of the outside? 18 times 3, 54 something to the 17th? Is that the derivative of the outside? Yeah, we multiply 18 out front, then subtract 1. So that's it. That's the derivative of the outside. And what should we do to the inside? Leave it alone. But then we're going to multiply times the derivative of the inside. And what is the derivative of the inside?
Negative 24x
The negative 24x to the squared
minus 40x.
to the 7th? Yep, that's it, folks. In this particular case, there's nothing we can simplify. Or is there? Can we simplify? Can we FOIL these two terms together?
No, because this one's to the power of 17.
Yeah, this one's being raised to the power of 17, so we cannot just FOIL these together. And so that forces us to be done. How convenient. How nice that that's being raised to the power of 17. Because now we cannot multiply those together. We're done. In a textbook, you might see the final answer written down differently, though, because even though we can't take anything out of here because it's being raised to the power of 17, what can we take out of here? We could take out a negative 8x squared. So really, I'd have 54 times negative 8x squared. And that was outside of this part, which is now 3 plus 5x to the 5th, all being multiplied by this thing, which is negative 8x cubed minus 5x to the 8th, all to the power of 17. There, did I do that right so far? So far. I took a negative 8x squared out of that last one. So that'd be negative 24x squared, that'd be
It would be
negative.
positive 8x cubed for the second. And so take out the 8x. Oh.
This is still this one. I didn't do anything with this
I'm
one.
looking at the.
But this one, I took out, well, I chose to take out a negative 8.
Oh yeah, I was gonna throw one.
Oh, okay. All right, so then from here, I could go ahead and multiply the 54 times the 8, which would be what, negative 432 x squared times 3 plus 5 x to the 5th, and then that last thing. But honestly, folks, this answer is just fine. You know, we could spend a lot of time trying to simplify things, and sometimes even after you mess around with simplifying for a while, does that really look any better? Not much, right? So that's a really tough one. I'm going to give you a weird instruction. Simplify if it will make it look better. But if simplifying really doesn't get you anywhere better, then we could leave it in our final answer. The tough thing is, how do you know if something's going to simplify well or not unless you do it? Right? That kind of leaves you in a pickle. I suppose that means simplify everything. But in this case, nothing is going to simplify that much. Oh, we did the chain rule. So let's try the chain rule again. This one, number 3, says that f of x is, and I'll go ahead and write this down immediately as my outside function and my inside function. The outside function is something to the negative 3. And the inside function is 2x plus 4. Did I do that right?
I just have a random question.
Yeah, go ahead.
What if somebody was like we were doing the test and we were going to leave it like that, but we just decided just for whatever to just simplify it, but we simplified it wrong? Would you take the other one? Or would you
I don't think I would take out points for that.
Okay.
Because this is the right answer. Yeah. Okay, so there we have it, folks. We want to take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. So what's the derivative of the outside? Let's see here. I'm going to keep calling on people. James, I won't call on you yet because you just got here. I've already spoken to you folks. Luis, what's the derivative of the outside? Yeah, -3 something to the... Yeah, very good. That's the derivative of the outside. And what should I do to the inside, Luis?
Leave it alone.
Leave it alone. And then we multiply by the derivative of the inside. What's the derivative of the inside, Elias? 2. Just 2. Now, should we simplify this one? Yeah, absolutely. We could make this one look better because all we have to do is multiply the 2 times the -3. And this one definitely looks better by simplifying it. In fact, can't we simplify it more? What would a really clean final answer look like? We never want to leave our answer with a negative exponent, so instead, let's drop it down into the denominator. There. That's a really nice, clean answer. Just for the sake of showing it to you, could I simplify the denominator more? Yeah, I could factor out, right? And so I'm just going to show it to you for the sake of showing it to you because we do a lot of simplifying in here. I could take a 2 out of the 2x plus 4, so it's really 2x plus 2. But both of those are being raised to the 4th power. So how do I deal with that exponent? It goes on to both of them, right? So it's going to be 2 to the 4th and x plus 2 to the 4th. So that's 2 to the 4th and x plus 2 to the 4th. Did I do that correctly? Because that's a technique we might want to use again. A simplification technique. So I rewrite 2x plus 4 as 2 times x plus 2. And then I'll put my exponent on both the 2 and on the x plus 2 to get 2 to the 4th x plus 2 to the 4th. Because now 2 to the 4th is 2, 4, 8, 16. So now I have -6 over 16 x plus 2 to the 4th. And now what can I do? I can keep simplifying now my coefficients. So this really was a good thing. I can divide a 2 into both of those. So 2 goes in there 8, 2 goes in there 3. And now we have -3 over 8x plus 2. Now are we done? Yeah, now we're done. There's something funny that goes on in calculus because part of the time you're doing calculus. So there, that's where we did calculus. What do we do for the rest of the time? Algebra. All right, so that does feel a little funny. It'd be funny if there was like a T-shirt or something like, sure, I want to do calculus, but only the calculus part. Right? Because the calculus part, that's the new skill that we're actually learning. And all this simplification business is stuff we've been doing for years. It's just a matter of cleaning up our answer so it looks good. All right. Well, let's try another one. Oh, good. All right. So what we're about to look at next is a couple other functions, such as e to the x and natural log of x. So let's remind ourselves. We did just remind ourselves about this one. What's the derivative of e to the x? E to the x. So that's one formula we definitely want to know. One we've only done once so far is what's the derivative of the natural log of x? The derivative of natural log of x is simply 1 over x. That is 1 over the argument. And we're about to see what that really means in context. So these are 2 rules that we're going to start using more. So let's go ahead and try the first one. use the chain rule to find the derivative of 5. So f of x equals 5 e to the
2x
2x to the 7th
minus 2x.
minus 2x to the 8th. Okay, so here's the question. What's the outside function? What's the inside function? Maybe the question is easier asked. What's the inside function?
The 5e?
Not
No,
the 5e.
the 2x.
The 2x to the 7th minus 2x to the 8th. So if I were to write this again, I would write this as 5e to the something is my outside function, and 2x to the 7th minus 2x to the 8th is my inside function. If that doesn't resonate with you just yet, just keep on looking at it and ponder, why would the e to the be the outside function? And why would the 2x to the 7th minus 2x to the 8th be the inside function? And it might be easier to think about which one did you plug into the other. You know, if 5e to the something is one function, and 2x to the 7th minus 2x to the 8th is another thing, what function just got plugged into the other function? And the answer is that the blue one got plugged into the green one. The blue function got plugged into 5e to the. So we would say that the outside function is 5e to the something. And then what did we plug into it? 2x to the 7th minus 2x to the 8th. That's how you answer the question about outside and inside. Outside is the function that's about to get plugged into, and inside is the function that got plugged in. Okay, so then, how do we take the derivative? How does the chain rule work?
5e.
We take the derivative of the outside and leave the inside alone. So what's the derivative of 5e to the x? Just 5e to the x. The derivative of e to the x is just e to the x, and a coefficient comes along to the right. So the derivative of 5e to the something is just 5e to the something. And what do we do with the inside function? We leave it alone. But then we multiply by. So I know it looks like nothing happened, and that's because nothing happened. The derivative of the outside is still 5e to the, and we left the inside alone. But now we're going to multiply by the derivative of the inside function. What's the derivative of the inside function?
14x.
Yeah, 14x to the 6th minus 16x to the 7th. There. So that's what it looks like. As you write down your final answer, you really want to exaggerate the sizes of these fonts. So 5 is a normal size number, e is a normal size letter. The exponent 2x to the 7th minus 2x to the 8th, that's teeny tiny, that's an exponent. And then that whole thing now gets multiplied by large, regular sized function information. Right there. Right here I did a really good job of exaggerating the fact that this binomial is an exponent. It's tiny and up high. This binomial is a regular binomial that's getting multiplied by the whole thing. It's large and regular sized. If we wanted to make this look a little better, we could call this 5 times 14x to the 6th minus 16x to the 7th, all times e to the power of 2x to the 7th minus 2x to the 8th. That might feel a little better. I guess the key thing is here we have 3 terms. We have a 5, we have an e to the, and we have a binomial. Now, could I simplify this further? And by simplify, we just mean factor. Can I factor anything out of here? 2 x to the 6th. I can take out a 2x to the 6th. So now I have a 5, a 2x to the 6th, outside of 7 minus 8x, all e to the 2x to the 7th minus 2x to the 8th. So now what do we have? 10x to the 6th times 7 minus 8x times e to the power of 2x to the 7th minus 2x to the 8th. Now, right now, you might be asking yourself, Mr. G, take another look at that problem. Here is the original problem statement. Here was the calculus. Here was the simplification. How do you feel about that? That this is just the statement of the problem. This is the calculus part. And then this is the simplification part.
The simplifying is like the.
Yeah, I mean, that's pretty wild, right? So part of what we do in calculus is we perform the derivative so that we go from a function to a derivative. But then it's a matter of simplifying the final product to give it to somebody else. The end user, whoever's going to then use that derivative. And I suppose I should at the very end write f prime of x equals all that. All right. Well, I guess I could have kept that up for a while. Ready for another one? All right, this next one. Oh, good. And then we still have a few. I don't know if we can get to all these. Whoa, is that really all part of this one? Okay, we're definitely not going to get to all these. But let's go and try this next one. 5. So, what is the derivative of the natural log of x squared? X squared plus 4x plus 5. First of all, do you see the outside function and the inside function? What is the outside function?
Yeah.
Yeah, the ln is the outside function, and the inside function is x squared plus 4x plus 1. How do we take the derivative of the natural log? It's just 1 over the argument. So whatever that thing inside the natural log is, it's 1 over that. So starting, the derivative is the natural log, the derivative is 1 over whatever is in there. You take the derivative of the outside, leave the inside alone, and then multiply by the derivative of the inside. So the derivative of the outside would just be 1 over x squared plus 4x plus 5. And that was us leaving it alone. Right? So the derivative of natural log is 1 over the argument, leaving it alone. And then you multiply by what?
The derivative.
The derivative of the inside. And notice, since this is a fraction, where am I about to put the derivative of the inside? Up in the numerator, right? I don't want to accidentally multiply it times the denominator. It's up in the numerator. I'm taking this whole thing, and I'm multiplying it by the derivative of x squared plus 4x plus 5, which is 2x plus 4. That part goes in the numerator. So the derivative of natural logarithm is the fraction 1 over the argument. But then I'm going to multiply that times the derivative of the inside function, which is 2x plus 4. So that's really over 1. That way we keep our numerators and denominators correct. So what is our derivative then? 2x plus 4 over x squared plus 4x plus 5? I immediately put an equal sign there. Do we need to go further? Can anything else be done? Can we?
Yeah.
We can? What multiplies to make 5 that adds to make 4? But it's good to ask the question. It's good to try. If you could have, you should have. But we can't. If we did anything, we could have changed that to 2x plus 2 over x squared plus 4x plus 5. And that would be nice and simplified as well. Now, in this case, it wasn't so extreme, right? The problem statement took 1 line, the calculus took 1 line, the simplification took 1 line. So it's not quite as it takes a line, the calculus takes a line, and then simplifying takes 1, 2, 3, 4 lines. Was that it from there? Yeah, that was it from there. Wait, was it really from there? Yeah, that was it. Okay. So this next question is graphical. Oh, I guess this is actually a couple questions. Okay, number 6. Ah. Oh, there we go. Yes. 2 graphs. This is number 6 over here. That over there is a different problem, number 7. So right now for number 6, they're saying if f of x is really g of x divided by h of x. So what rule is this? Product, quotient, or chain?
Quotient.
Quotient rule. Then what's the derivative with a 3 plugged in. So how do we take the derivative of a fraction or a quotient? Hody hi minus Heidi ho over ho ho. So let's start by doing that. They tell us that we're using f of x is equal to g of x over h of x. So let's take that and go ahead and write down the quotient rule. The quotient rule would be d high. Did I do that right so far? O d high minus high d ho. Is that correct? Is that O d high minus high d ho? All over ho ho? And what did they want us to find? F prime. So now we have to go find all those things. H of 3, G prime of 3, G of 3, H prime of 3, and H of 3 squared. Where do we go find all those values? Yeah, just from the graph, by looking at our graph. So I'm going to replace all that with parentheses, and we're going to go to our graph and go find all those values. Which values would be the easiest to find? The non-primes or the primes? Yeah, probably the non-primes, because those we just look up from the graph itself. So for instance, what's h of 3? Here's my h graph, and I want h of 3, which is a 4.5. So this is my h function. I'm going to plug in 3, and the answer is 4.5. So h of 3 is 4.5. What's another one that would be easy to find? Oh, actually, h of 3 is my denominator as well, isn't it? There we go. What else would be easy to find? G of 3? Yeah. So we come over here to my G graph, and I want G of 3, so I plug in 3, I look up, and what is it? 3. Also 3. So now I know that G of 3 is also 3. All right. Well, now I need to find G prime of 3 and H prime of 3. I'll start with G prime of 3. What's G prime of 3? What is it even asking for? G prime means you're looking for the slope. So what is the slope right here? We can calculate it. What's our graph doing?
3.
Up one, right one, up one, right one, up one, right one. So it's just 1 over 1. It's just 1. So G prime of 3 is just 1. But now what about H prime of 3? The last value we need. Well, here's H prime. Here's H, and here's 3. What's our slope right there? Negative what? We really have to look at our scale. That's 1 unit. The box is 1 unit tall, and a box is 1 unit. If we start here, yeah, isn't it negative 1? It'd be down a half, right a half, down a half, right a half, down a half, right a half. So down 1, right 1? Yeah. Okay, we did it. I mean, we have to compute that, but we did it. That was what they were asking us to do. So that would be 4.5 plus 3 over 4.5 squared. So 7.5 over 4.5 squared, which is what? Did anyone else get 0.370? Repeating. Did anyone else get that?
3.0?
Yeah, 0.370 repeating. Anyone else? Yeah, Ashley, you got that? Okay. All right. So you'll notice that Math AS gives us these interesting questions like this one with the table, and then this one with the graph. And it's because ultimately you're just using the definition and then plugging in a bunch of values. Okay, so hold on, don't go anywhere just yet. Number 7, I don't think, yeah, number 7 wasn't related to those pictures. So let's take a look at where we are here. I still want to go through and do, oh, definitely 8 and 9. In fact, maybe I'll do one of those right now. Oh, yeah, that one would have been good. And then we have these fellas. Okay, so I need a little bit more time to do these with you. Let's go ahead and skip 7. In fact, you can cross 7 out. Just cross 7 out. I'll take it out. Well, let's go ahead and take a look at number 8. We still have a couple minutes here. Class is still going. Let's take a look at number 8. So everyone crossed out number 7? I'm fine with that. All right, number 8. How do we take the derivative? First of all, what's the outside function?
Square.
The square root. And the inside function is the x squared plus 3x plus 7. But we can't actually take this derivative of a square root. What do you have to do? Rewrite the square root as?
Squared.
Not squared. To the 1/2. So when you take the derivative of a square root of something, you have to first rewrite it as.
Is it a 2x squared?
You're right. 2x squared plus 3x plus 7. Thank you. So the outside function is parenthesis to the 1/2. The inside function is the polynomial. Okay, so now we can go ahead and take this derivative. So how do you take the derivative of the outside function? The outside function is just the power rule. So Rosa, go ahead. What do I multiply out from?
1/2.
1/2, and then subtract 1.
So it'll be negative.
Yeah, and instead of subtracting 1, I'll subtract 2 halves, so that's a negative 1/2. Very good. So that's the derivative of the outside function. And what do I do to the inside function?
Leave it.
Leave it alone. But then I multiply by the derivative of the inside function. And Karina, what's the derivative of the inside function?
4x.
Yeah?
3.
Yep, 4x plus 3. Now this can be simplified significantly, as in we should. So notice that I have a fraction, which is already a numerator and a denominator. I have a negative exponent, which means you have to push it down into the denominator. And then this term is just a binomial. It'll stay in the numerator. So I'm going to start by making myself a nice big fraction and putting the things where they should go. So my 1/2, I'll put the 1 up top and the 2 down below. This big trinomial with the negative 1/2, that drops down to the bottom. 2x squared plus 3x plus 7, all to the power of 1/2. And then my 4x plus 3, that stays up top. So that's convenient to just think about, does it go in the numerator or does it go in the denominator? And we can clean this up one more time because what's to the 1/2 mean? Square root. So we really have 4/2, the big square root of 2x squared plus 3x plus 7. And that looks good. That's a nice, clean, final answer. And in fact, number 9 is going to work out very similarly to that.
Until you find out.
Oh, and then they want us to find something, f prime of 4. So since that's our f prime, what do? Just plug in 4. And when you plug in 4, what should you use? Your calculator. You know, just bust out your calculator. So 16 plus 3 is 19, all over 2 times the square root of 4 squared 6, 32 plus 12 is 44 plus 7 is 51. Did anyone else get 19 over 2 at 51? The Math AS I'm assuming they'll take that, but they might not if you have to rationalize the denominator. Are you allowed to leave a square root in the denominator? Not technically, you're not supposed to. So you'd have to multiply top and bottom by root 51. And then you'd have 19 root 51 all over 102. Did I do a computation wrong? Was that correct? Ashley, did you get 51? Oh, you just typed it all in and got a decimal. Okay, that's another way you can do it, folks. Just type it all in and get a decimal. Okay, now before anybody leaves here, let's just go back to the calendar here real quick. Today, so on the 22nd, that's our review day. And I didn't bring the practice test for you. Today, I'll go back to my office right now and email you a PDF of the practice test. But then when you come to class on the 22nd, we're going to finish these and then look at the practice test. Okay, so that's what we're doing on Thursday. We'll finish this lesson that we were just doing, and we'll look at the practice test together. So when I email you the practice test today, definitely pull it up on your computer, look at all the problems, print it out if you can, but I'll bring you a hard copy on Thursday. And then the test is next week on Tuesday. Okay, no? You don't have to worry about finishing the rest of this packet right now. If you want to try, 10 and 11 and 12 and all those, you can. You don't have to. I'm going to go over it with you on Thursday. So I would focus on your homework tonight would be going on to Math AS and doing everything up until where we are now. All right, well, thanks, folks.
2.5 is going to be due
next week on the day of the test.
Both A and B?
Yep, well, baby. Yeah, the test will cover all chapter 2 up until now. Yeah.
Can you just explain to me the number 1 again?
Yeah.